Welcome to Deep Engineering's YouTube channel, where we bring you real-world insights from the engineers and authors shaping the future of software. Today, we are speaking with Professor Elías Combarro, co-author of two books with PACT, A Practical Guide to Quantum Machine Learning and Quantum Optimization, and the more recently published A Practical Guide to Quantum Computing. Elías is a full professor in the Department of Computer Science at the University of Oviedo in Spain. He holds degrees in both mathematics and computer science, earning national academic honors in each. He completed his PhD in mathematics in 2001 with research spanning computability, theory and logic, and has since authored more than 50 papers across quantum computing, algebra, machine learning, and fuzzy systems. His recent work focuses on applying quantum computing to problems in optimization and algebraic structures. Elías has held research appointments at CERN and Harvard and represented Spain on the advisory board of the CERN Quantum Technology Initiative from 2021 to 2024. Today, he's here with us to talk about his second book, but more broadly about the foundational ideas behind quantum algorithms, the challenges of quantum programming, and how software professionals can begin to engage with this fast-moving field. A very warm welcome to you, Elías. Thank you for being here with us today.
Thank you for having me. I'm really excited about this.
Okay, then. So let's get started. We'll start by talking about your second book, A Practical Guide to Quantum Computing, which focuses on foundational algorithms like Shor's and Grover's. And this is in contrast to your first book, which focused on variational methods and quantum optimization. So what prompted this decision to go back to basics with your second book?
Yeah, I would say that there are two main reasons for going back to these foundational algorithms in quantum computing with our second book. The first one is that, well, we kind of wanted to include these algorithms in the first book, but it was impossible. I mean, if you have read the book is almost 700 pages long, which was much more than we expected when we started writing. So it was nearly impossible to include any other content. So we were always thinking, we should have somehow accommodated these very important algorithms in the book. It was not possible. So we always had this idea to come back and maybe write another book or an extended edition or something, including these algorithms, which are very, very important in quantum computing. And they are probably like the first algorithms that everybody that starts with quantum computing studies at the very beginning. But we decided to go with more modern algorithms, like algorithms for optimization and machine learning in our first book, because this is a hot topic. And at the time, there were mainly no books covering this, and we thought it was important to focus on these modern algorithms. But then, in addition to this desire to write something about these algorithms, new courses in our university and in many other institutions are being introduced for quantum computing. I'm teaching now currently 2 different courses, and maybe a third is coming next year. So we felt the need to have some textbook for these courses because they include part of what is covered in our book on quantum machine learning and optimization, but also foundational algorithms like Shor's, Grover's, and other protocols like quantum teleportation or quantum key distribution, which are kind of different to machine learning and optimization. Maybe we will discuss something about this later, but they are also very important. So we felt the need, the inner desire to write a book on this. And also it was very useful for us to have this kind of material ready for our students and for anyone, anywhere in the world that wants to be introduced to quantum computing.
Right, got it. And was there any feedback that you received for your first book that influenced your approach in terms of pedagogy or technical depth in the second book, which is more foundational?
Well, I must start by saying that we were overwhelmed by the reception of the book. I mean, we are still, even yesterday, I received a message from a master student here in Spain. I never met him. I have never met him, but he wrote me to say that he was defending his master thesis in quantum machine learning, and that one of the main influences for him to choose this topic of research was our book. So this is just one example of the many messages we have received from readers, all of them extremely positive. So we are really overwhelmed and super happy with the reception of the book. And I think the only or the main problem, if we can call that a problem, with our first book is that we had a lot of code intertwined with the explanation of the concepts and the algorithms because, well, we are kind of hand-on guys. We like to learn by doing. So we think that this is very convenient, that you can just fire up your Anaconda, your Jupyter Lab application and run some lines of code and nail and drive home the concept that you are reading about. Okay, so this was our approach. But this has a drawback when you are studying quantum computing. And this is that the software, the libraries, the package evolve very rapidly. So they change very rapidly, and then you need to keep up to date with the new versions. And some of the code may become dated and may require some small modifications for it to work. So this was something that we discovered after we published the book. Okay, people find it very useful that you have the code together with the explanations, but at the same time, it's more difficult to update the contents and to update the book because it's completely intertwined with the explanation. So in this new book, we have decided to somehow extract the code and devote chapters only to code and chapters only to explanations. So you can learn about the algorithm and then go to the chapter with the code and learn how to program the algorithm or the protocol, how to modify, do some exercises to learn more about how it works. But at the same time, it's easier to isolate changes in the code because they are not intertwined with the book. So I think that is the main lesson that we learned from the first book. I still think that both approaches are nice and are useful for students, but probably it's easier for someone who wants to read this book maybe 2, 3, 4, 5 years from now to learn the algorithm and then update the code because we will be publishing any modifications to the notebooks online, so it's easier to keep up with the changes.
Yeah, and in many ways, the second book is like a prequel, isn't it, to the second book, for those who may find it more challenging to just start with that. And even in this second book, like you said, you're both very hands-on authors, and that's the kind of approach you've used with this book as well, and you've used Qiskit throughout. So what made Qiskit the right choice for teaching foundational quantum computing for you?
Well, this was a difficult decision because nowadays there are several, so to say, quantum programming languages. They are not full-fledged full-fledged programming languages. They are more like packages or libraries, but there are several to choose from. All of them are nice, and all of them have their advantages and their drawbacks. And in fact, in our first book, we included 3 different languages. Qiskit, of course, but also PennyLane and also D-Waves Ocean, because we were focusing on quantum machine learning, for which PennyLane is, I think, even better than Qiskit. To program these deep wave quantum annealers, you need D-Waves Ocean. There is no other way of accessing these machines. But in this book, we are going back to the basics. So it was more useful to have just one language. We don't need 3 of them or 2 of them, because for these foundational algorithms, almost any quantum programming language it's enough. But at the same time, Qiskit is the one that has the biggest number of features And it's also the one that makes it easier to access quantum computers online. And for us, this is also very important that you can, well, work with locally in your own laptop or computer with these simulators, which are not real quantum computers. It's just a simulation of what a quantum computer can do. But at the same time, it's nice to be able to access actual quantum computers online. And this is something that you can do with Qiskit very, very easy. And for instance, one of the exercises that we propose to the readers of our book is to take some of the protocols after running them locally on simulators, run them on quantum computers. And you only need to change like 3 or 4 lines of code, but it's very satisfying to, well, be able to say, I'm running this on an actual quantum computer. And for instance, I particularly like one of them, one of these exercises. I've done this in several courses with the students and they love it. This is the protocol to explore whether nature is quantum or is classical. This is based on something that is called the CHSH game that we explain in full detail in the book. And then we give the code and we ask the readers to run this on a quantum computer. And when you run this on a quantum computer, you get a figure of merit, which is the number, the ratio of times that you win this game. And this is well above what you can do with just a classical computer. So to me, this is, and you can do it yourself. And the people that the researchers, the physicists that first did this kind of experiment won the Nobel Prize in, I think it was 2022 for this kind of experiment. So now you can do it just with your laptop connected to the internet because you send this code to a quantum computer. And to me, that is kind of fascinating.
Yeah. And then, I mean, you made quantum computing accessible with this choice, I think, to keep it short. Okay, thank you for that. Now let's move on to our next segment and talk a bit about core quantum concept. So, my first question is, how should software developers think about a single qubit and its state? For example, why the block sphere, state vector representation. And how does this view change when extending to 2 or more qubits?
Yeah, this is a very important question because when you think about qubits and their states, especially when you have a big number of qubits, which is the case with actual quantum computers nowadays, intuition is not really very helpful. Okay, so when you think about one of these quantum computers that you can access online, they have 127 qubits, for instance, that the ones that are available to use for free. And this means that you are working with 2 to the 127 numbers implicitly. This is such a huge number that is very, very difficult to conceive. So intuition about this kind of a structure is really not very easy to combat. So when you have just one qubit, you have this nice geometrical representation that is called, as you mentioned, the block sphere. I must say I'm not a geometrical figure. To me, geometry is not something that I have a great intuition about. So I prefer like symbolic representations and algebraic manipulations. But for one qubit, you have this block sphere that represents every point in the surface of the sphere is a possible state for your qubit. And then quantum operations, what we call quantum gates, are just ways of rotating this sphere. So this is a nice way of visualizing what is going on with the state of your qubit when you apply one of these operations. Alternatively, what I prefer is to think about this as a regular vector of, in this case, complex numbers, but for most of the book, you can just think of real numbers. So a big vector of real numbers. This works, of course, for one qubit. In this case, you only need 2 numbers. And then for a bigger system with more qubits, you think about a vector And this is the main representation that we use throughout the book. And the state of the system is just a vector of numbers. And then any operation that you perform on these numbers is the multiplication of a matrix times this vector. And to me, this is like the most useful way of thinking about the operations that are going on in the computer. Of course, there are other representations, geometrical representations that extend beyond one qubit, but to me, they are more exotic than really helpful. But maybe that's because I'm not a geometrical thinker. In any case, what I would like to say, and I always tell this to my students, the amount of mathematics that you need in order to start working with quantum computing is surprisingly reduced. You only need to know what a vector is, what a matrix is, and how to multiply a matrix times a vector. And even if you don't know this, we cover this in one of the appendices of the book. So it's not about knowing a lot of advanced mathematics or physics. You can start right away if you know what a matrix and a vector are.
Okay, got it. So, follow-up I had with this was, what does an entangled 2-qubit state look like in this representation? Why can't it be factored into independent single-qubit states?
Yeah, this is a very surprising fact about quantum systems. The thing is that entangled systems cannot be described by the state of the individual parts. So you can have a system with 2 qubits, and both of them have like a global state that describes the state of the two systems. But if you look at any of them in isolation, you cannot, by putting together the description of the state of these qubits in isolation, reconstruct the whole state of the system. You need to know the global state. This is why you need these 2 to the n amplitudes, because otherwise you would need only 2 numbers for each of the parts, but then the correlations between the parts are described by the other numbers that are not like locally encoded by the qubits. So this is something that was very surprising in the early days of quantum physics, that this idea of entanglement could be something real. Even Einstein was baffled by this. He called this the spooky action at a distance, because when you have 2 entangled qubits or 2 entangled particles or system with entangled parts in quantum theory, modifications in one of the parts immediately affect the other part, even if they are very, very far away. And as you know, Einstein was the developer of general relativity, and in general relativity, there is a limit to the speed in which information and interactions can travel throughout space. So this kind of happens instantaneously, and this was like, whoa, this is something really, really spooky, really, really strange. But this has been confirmed by experiment every time that it was tested. Even this CH-SH game that I was mentioning earlier is about this property of entanglement. So this idea of representing states individually, for instance, with Bloch spheres, are not good for states with more qubits. So that is why I think that using the vectors is more useful, because then you have a mathematical way of checking whether a state is entangled or not, whether we can describe it by taking a look at each of the parts individually. And this is exactly what you were mentioning about the possibility of factoring the state. Because when the state is not entangled, then you can describe each part individually, and then when you multiply back these numbers, you obtain the description of the whole state. But if the state is entangled, it's not a product state, you cannot do this. There is no way of like multiplying back or composing back the description of the qubits and of the individual qubits to obtain the results.
Right. And can we talk a little bit about, leading on from this, why entanglement is considered such a crucial resource in quantum algorithms?
Yeah, because this kind of property only happens with quantum systems. This does not happen in classical physics. But you can exploit this to implement different protocols and algorithms that are simply not possible with just classical resources. We describe some of them in the book. For instance, how to create or how to send information in what is called super dense coding, or how to teleport quantum states. And for this kind of application, you really need entangled states. You really need this idea of entanglement. You cannot do this with classical resources alone. So this is one of the applications from the point of view of quantum information science, quantum computing, that you can really not do with only with classical resources. And this can be, for instance, the one of the central concepts in a future quantum internet. Because with this quantum entanglement, you can teleport states, and this can be useful to communicate over long distances. So this kind of idea is, or protocol is one of the ways in which you can exploit entanglement for practical applications.
Got it. Now let's talk a little bit about quantum measurement. In what fundamental way does measuring a qubit differ from reading a classical bit?
Well, this is one of the things that I think for students or for people that start learning about quantum computing and quantum physics in general is one of the most surprising things. Because, for instance, in classical computing, you take for granted that you can always obtain results by just taking a look at your variables or at your data. So if you have some structures, data structures, vectors or lists or trees or whatever, you can always inspect these structures and obtain all the information about the data. This is not so in quantum computing. In quantum computing, you have these states in superposition, maybe with entanglement, described by this a big amount of numbers that we were talking about before. But when you measure them, you cannot obtain all these numbers. You only obtain partial information about this. Okay, so for instance, if you have a quantum state with just one qubit, this is described by two real numbers, let's say, two complex numbers, two real numbers. So in principle, there is an infinite amount of information because real numbers can have an infinite number of decimals. But you cannot access this. You can only access one bit of information. In order to do this, you need to perform a measurement. And then the state will collapse probabilistically to either 0 or 1. So when you are not measuring the qubit, it is in a state which is a superposition, so it's part 0, part 1. When you measure it, it kind of decides whether it is in state 0 or state 1, and then it collapses. You lose all the information about the previous state. If you measure the qubit and you get 0 as a result, then if you subsequently measure the state again, it is 0. Okay? You won't be able to retrieve the information that the state had before your measure. So when you measure the system, you completely change its state. And at the same time, this result is probabilistic. So if you run an algorithm and you use exactly the same input data, you measure the results, you run this algorithm again with the same input data, you may obtain a different result, which is kind of very, very strange for computer scientists or for people who use classical computation. How is it possible that I run the same algorithm with the same input data and I obtain different results? This is similar to some classical algorithms that use randomness, like genetic algorithms or things like that, that resort to some kind of pseudo-random number generation. But in this case, this probabilistic behavior is not something that you kind of simulate. It's integral to quantum computing. You cannot get rid of this. This is a fundamental property of quantum computing. So quantum measurements are different from classical retrieval of data in two different ways. The result is probabilistic, so many times you will have to repeat your experiments and then perform some statistical computation with the data, and it alters the state of your system. You cannot like measure the same system several times to try to retrieve information, because once that you measure the system, you lose all the rest of the information.
Right. And how would you say developers can decide which qubits to measure and at what points in a circuit?
Well, it depends on the algorithm or the application that you have in mind. But until recently, in fact, with actual quantum computers, you could only measure qubits at the end, which may seem like kind of a limitation, but it really is not, because we have this theory or this theorem in quantum computing that, well, if you need to measure something in the middle of the execution of an algorithm, you can do that, but it's really not very different from deferring the measurement until the end and then like collect all the data from the end. So anything that you can do with mid-circuit measurements, you can also do with measurements at the end. In fact, now it is possible, for instance, with Qiskit, to measure some of the qubits in the middle of the execution of an algorithm of a circuit. But it's really not very, very important, because you can always defer all your measurements to the end.
Right. And you were talking about, just now about the randomness introduced by measurement. So, what strategies, according to you, can help manage this randomness introduced by measurement?
Well, we must first distinguish between two different sources of randomness. One is this intrinsic randomness because of the probabilistic nature of measurements in quantum theory. And this is something that we inherit in quantum computing, and we cannot get rid of this. To deal with this kind of randomness, you need to do some kind of statistical analysis of your results after repeating the same algorithm, the execution of your circuit several times. So for instance, imagine that you are trying to determine whether a certain element with a certain property is present in a vector. You are looking for an element in a vector. For instance, you have information about your clients in a database, and you want to find whether there is any client from, I don't know, from Spain, let's say. So in this case, we have Grover's algorithm, which is one of the main algorithms that we cover in the book. And you only have a probabilistic guarantee of finding the element, even if it exists. This guarantee can be quite high, like 99%, for instance, but you may be unlucky. And if you run your algorithm just one time, maybe you don't find the element that you're looking for. So what you do is you repeat the algorithm several times, and you keep like the best measure, okay? Or for instance, in our previous book, we were working with quantum machine learning. Maybe you want to classify an image as either representing a cat or a dog, okay? And then when you measure your qubits, 0 means that it's a cat and 1 means that it's a dog, okay? If you measure just once, since this is probabilistic, you can never be sure. But if you repeat this, let's say 100 times, and you keep the result that you obtain the highest number of times. For instance, 70 times it was 0, 30 times it was 1. Then by voting, you decide that this is a top, because the majority of results were in favor of tops. Okay, so this is the way in which you deal with intrinsic randomness. Okay, or for instance, if you are trying to estimate a number, this is something that we also do in the book with something that is called quantum phase estimation, that is very important in many different domains. What you do is you repeat this in order to have better and better estimations. Then you compute kind of an average, and the biggest the number of repetitions, the more accurate your estimations. So this is one source of randomness, the intrinsic probabilistic nature of quantum theories. But with actual quantum computers, you also have randomness coming from imperfect operations, from noise, from interaction with the environment. In our book, for most of it, we work with ideal versions of quantum computers in which we don't have this kind of noise. But then in the last part of the book, we also introduce a very short introduction to quantum error correction and how you can deal with this fact that quantum computers nowadays are not perfect. So this noise needs also to be taken into account, especially if you are working with actual quantum computers. And for this, there are different techniques. There are techniques like error mitigation, in which you first kind of calibrate the computer. So you set the states to 0, 1, and you measure how many times you obtain errors with this. And with this information, you can correct your measurements. And then there is quantum error correction that is more sophisticated and more difficult to implement, but it's better to try to deal with these nodes.
Right. Okay. Thank you for that brilliant and very clear insight, Elias. Now let's move on to talking a little bit about some key quantum algorithms, starting with Grover's algorithm. Grover's algorithm offers a quadratic speedup for unstructured search. Could you explain the core idea of amplitude amplification in Grover's algorithm and what assumptions or resources it requires?
Mm-hmm. Yeah, I must say that Grover's algorithm is probably my favorite quantum algorithm, because at the same time is mathematically beautiful. From a computer science point of view, it's very surprising, because the main idea is that you have this information, for instance, in a vector, as I was mentioning earlier, and you want to find some of the elements in this vector that satisfy some property that you are interested in. So if this data is not ordered in any way, imagine, for instance, that you have a dictionary of words, okay? But they are not ordered. They are in completely random order. And you want to find one of these words. What can you do? If the dictionary is ordered, you know that you can start approximately in half of the dictionary and then see if your word goes before or after, and then you go to the first part or the second part and you repeat, and then you quickly find the place in which the word is located. But if the words are completely at random with a classical algorithm, the only thing that you can do is go one by one and try to find. And if it is not in the vector, you will need to look at all the elements to check that it's not there. And if you are not very lucky and it is in the last part of the vector, you will read a lot of them in order to find. But with Grover's algorithm, even if the data is not ordered at all, you can find the element that you are looking for very quick, or much more quickly than with this idea. Because, for instance, if you have 1 million elements in your vector, with a classical computer, in the worst case, you will need to query 1 million times the vector. With Grover's algorithm, you only need, because of this quadratic speedup, only need to check the vector 1,000 times. And this difference grows bigger and bigger with the size of the vector. So to me, this is incredible. How does this work? And this is where the beauty of quantum theory and mathematics comes into play. Because what you do here is to create this superposition. I've been talking about this idea of having like qubits in multiple states at the same time. So what you first do is you set your system in a superposition of all the possible elements. And then with this idea of amplitude amplification, what you do is you increase the probability of measuring the element that you want to obtain, that you want to find, step by step. Geometrically, and this is the most beautiful part from my point of view, this is kind of a rotation. So you want to measure this element and you start here, and one step at a time, you rotate the system until it aligns with the element that you want to measure. If you measure here, then you obtain the element. If you measure here, it's almost sure that you won't obtain the element. So you need to perform this for a certain number of steps that we detail in the book, and we give all the explanation, all the derivation. It's not very difficult, and it's quite intuitive in that sense. What is, to me, mind blowing is that if you perform more steps than you are supposed to do, then the probability of finding the element decreases, because you overshot and then you keep on rotating and then you go farther away from the element, which is something that in classical search algorithms makes no sense, because the more you search, the more probable is that you will find the element. But here, you cannot do too many queries to the vector, because then you ruin all your problems. So this is kind of, at the same time, surprising and very beautiful to me. But in order to apply this kind of algorithm, you were asking about the resources, you need to, and this is something that is quite common to most quantum algorithms, you need to transform the input to your problem into something that you can use with the quantum computer. Nowadays, we cannot access a hard drive, for instance, from a quantum computer directly to apply this algorithm. Maybe you have all your data in a file in your hard drive. Nowadays, you cannot access this. So you need to transform this into what is called an oracle, which is kind of an abstract function that you use in order to know whether you have found the element that you are interested in or not. So for instance, imagining that you are looking for, as I was mentioning previously, you are looking for a client from Spain. So what you do with this oracle is you give the oracle the index of one of your clients, the identification or the position in which the client is stored in the vector. And this oracle checks whether in that position there is a client from Spain, and it returns either true or false. This is the kind of resource that you need in order to use Grover's algorithm. All your search problems need to be mediated by this oracle. So you need to implement an oracle. This is something that we also cover in the book, how to implement oracles for using them in Grover's search for different kinds of problems.
Right. And yes, can Grover's technique be applied to problems beyond literal database search?
Yeah. For instance, one application that we did not cover in this book because we covered it in our previous book is to optimization. Because this idea of searching, of course, can be applied to search a particular element with a certain property, but also an element that minimizes or maximizes some criteria. For instance, imagine that you are looking again through the database of all your clients, and now you're looking for the client that spent the most money on your products last year. Okay, So you want to give him a present, or you want to contact him to say thank you or whatever. Okay. So in this case, you don't know what is the number, the amount of money that the person that was your best client spent last year. So you cannot search for a particular property, but you can always set like a threshold. Okay, so you know that, well, there are some clients that spend $1,000. So now you set your oracle, your search condition to only clients that spend $1,000 or more. Okay, so now that you have found all this, you can increase this threshold to $2,000. If there are still clients that satisfy this condition, then you can go to 3,000 or 5,000 or 10,000. So you keep iterating this search until you don't find any client above that threshold, and then you have the maximum. So this is an application that is called Grover Adaptive Search, because you are adapting your search criteria with each application of the method. And we've explained this in our previous book, but it's a straightforward application of the ideas of growers.
Right. And what are the current limitations of growers on near-term hardware?
Well, these limitations apply not only to Grover's algorithm, also to Shor's algorithm, and to most of the algorithms in this book. This is again one difference with the previous book. In the previous book, we covered algorithms that you can run nowadays in actual quantum computers and were designed specifically for modern for actual quantum computers, the ones that we have today. These algorithms are designed for ideal quantum computers with no noise. So any amount of noise is a kind of a limitation for the application of these algorithms. Why? Because they usually have a big number of operations. They have long circuits. All these algorithms are designed in terms of what we call quantum circuits, that are these operations that rotate qubits. So the more operations that you have, the more probable is that you have an error or that you have noise. And since you have a lot of them, then the probability of having errors and obtaining results that are not correct grows bigger and bigger with the number of gates. Also, actual current quantum computers are limited in connectivity. For all these algorithms, for instance, for Grover's search, you need operations that are applied to all the qubits at the same time. And this is something that you cannot do nowadays directly with a quantum computer. You need to decompose this operation in many small operations of 1 or 2 qubits. And maybe you cannot operate on 2 qubits that are far away in the device. So you need to introduce other operations to move the states around. So in the end, you end up with a lot of operations. And this is, if you run this for moderately high number of elements, for instance, to search for, then what you get is a lot of noise.
Right. Okay. So now let's talk about Shor's algorithm a little bit, which factors large integers exponentially faster than classical methods. Can you outline how Shor's algorithm uses period finding and the quantum Fourier transform to achieve the speed up?
Yeah. I must say that this is, like, to me, the most difficult part, or was the most difficult part to write in the book. This is, if I remember correctly, this is chapter 11, is almost at the end of the book. We build up all the way to this algorithm through the first 10 chapters. I remember that it was a challenge to write this chapter, because I studied this algorithm for many years, and to me, it's kind of second nature now to know how it works. But to go back to the mind of someone that has never seen this and to explain everything from first principles in a clear way was at the same time a lot of fun because it made me like rearrange everything and try to find the simplest way of explaining things, but at the same time it was a challenge. I think it's the longest chapter in the book. It was probably the most difficult to write. Having said this, I should mention that Shor's algorithm is super important because, well, when you hear that it's used to factor integers, this may not seem like something that is very exciting or very useful. But we must remember that the security of our communications on the internet, for instance, this kind of communication that we are having now, it's encrypted thanks to cryptographic protocols that rely on the fact that finding the factors of a large integer is very difficult for classical computers. So even if you have a very, very big computer, you would need millions of years to crack this encryption. If you have a quantum computer that can run Shor's algorithm, then you can break the security of the internet. And this is why governments and companies are advocating for the introduction of new cryptographic protocols that are resistant to quantum computers. Okay, having said this, the idea of Shor's algorithm, it's again mathematical in nature, and it has to do again with kind of rotations, periods, and things like this. As we detail in the book, in order to factor numbers, it's enough to be able to find what is called the period of a number. The period of a number is an exponent that you can raise the number to so that you go back to the beginning. So for instance, if you have number 2 and you raise it to 1, you have 2. If you raise it to 2, you have 4. If you raise it to 3, you have 8. But if you divide 8 by 7, the remainder is 1. So you are back to the beginning. So this kind of raising a number to a power and then taking the remainder is an operation that you need to factor numbers. What you get with this is a periodic function. It's a periodic function. Finding the period of this periodic function is equivalent to finding the factors of a number. And classical computers are not very good at this. They are very slow for this kind of operation. But with quantum computers, you can implement something that is called the quantum Fourier transform. Whenever you hear about Fourier transforms, this has to do with obtaining periods or frequencies of functions and data. For instance, Fourier transforms are used with digital signals for sounds to obtain the frequencies and represent this digitally and things like that. So quantum computers are very, very, very fast at doing this transformation, even for big numbers in which the periods are very difficult to find for classical computers. With this quantum Fourier transform, they can find the period very rapidly and then factor.
Okay. And what are the main challenges in implementing Shor's on today's quantum hardware?
Again, this is similar to what happens with Grover's algorithm. You need a lot of gates, so there is a lot of noise involved. And also for a practical application of these methods to factor big integers, you need to at least store the integer in the quantum computer. And we are talking, for instance, about cryptographic keys that are 2,000 or 3,000 or 4,000 bits long. So you need at least 2,000, 3,000, 4,000 qubits. The biggest quantum computers that we have today have at most maybe several hundred qubits, but they are imperfect. We need 2,000, 3,000, 4,000 perfect qubits. And in order to obtain these perfect qubits, you need a number of imperfect ones to construct quantum error correcting codes by repetition of information. So maybe to create one good logical qubit, one qubit that is resistant to errors, maybe you need 100 physical ones. So this goes up to several 100,000 qubits, which is far away from what we have today.
Right, right. And are there any smaller scale or simplified versions of Shor's algorithm that can be run on current hardware, or perhaps other quantum algorithms for number theoretic problems that might be practical sooner?
Yeah, in fact, in the last few weeks, I've read several scientific papers proposing simplifications of Shor's algorithm to reduce the number of qubits and to make it run in smaller quantum computers. But anyway, the number of qubits that you need is still far beyond what we have today. Regarding other number theoretic problems, there is this problem called Simon's problem, which is a completely academic problem. It has no application. But I read, I think it was yesterday or the day before, that some researchers have been able to run this in a reduced version of this in actual quantum computers, obtaining some advantage. But again, the problem is, and maybe we will talk a little bit also about quantum advantage later. The problem is that all these experiments in quantum advantage nowadays are still for problems that are academic, not practical, are very, very interesting to me, but have no practical use in the foreseeable future.
Right. Okay. Thank you for that, Elias. And we'll just take a small pause. I want to ask you, are you okay to continue for another hour? Because we've sort of reached only halfway to the question. Oh,
If it works for you, I'm happy to do it.
yeah, I'm fine. I'm really enjoying this. I'll just have a sip of water as well.
I told you I love talking, so no problem.
Yeah, no problem on that. Okay, then. Let's move on to next segment, which is about quantum error correction and quantum advantage. So quantum error correction, or QEC, is essential for scaling up quantum computers. What are the basic principles behind QEC? For instance, logical versus physical qubits, and so on.
Mm-hmm. So the idea of error correction in quantum computers is similar to the idea of error correction in classical computers. We are not aware of it, but in our classical computers, error correction is happening all the time. And mostly, oversimplifying, this happens by repetition of information. So imagine that you want to send information through the internet, through a noisy channel, and this information may become modified or corrupted during the transmission. Okay, so if you send just one bit, you send 0 or you send 1, you will never be sure that what the other party receives is exactly what you said, because this might be modified during transmission. But if, for instance, you send 3 bits all set to 0 or all set to 1, and you assume that the probability of one of them being modified is fairly small, then if one error occurs, the other person will receive maybe 2 zeros and 1 or 2 ones and a 0. And they'll know that some problem happened during the transmission. If they assume that, well, the most probable situation is that only one of them was modified, they can even correct the information and restore the message to what you intended to send. Now, if you do this instead of with 3 bits, you do it with 1,000, then you can reduce the probability of obtaining corrupted message as much as you want. You increase the number of bits, and then you reduce the probability of obtaining corrupted message. The idea with and this is exactly the same that with some modifications that we explain to some detail in the book. This is what we do with quantum computers. Instead of having just one qubit, we have many qubits representing the information. So each of the individual qubits in this bundle, in this group, is what we call a physical qubit. All of them together creating this redundancy is what we call a logical qubit, because it's not something physical, it's something that you construct, some abstraction of the state of these qubits, but they act as an ideal logical qubit. And again, we have this idea of, well, some of them may change their state, and in quantum computing, this is much more likely than in classical computers, because these qubits are very sensitive to external noise, so they can change their state very easily. And in order to know whether there has been some modification of the content of the qubits, because of what we were discussing before about measurements, you cannot measure the qubits. If you measure the qubits, you lose all the information. So you cannot do exactly the same that you would do in the classical setting. You cannot measure all of them and say, oh, one of them is different from the rest. I correct. No, because you lose all the information. Then what you do is a partial measure. Some of these qubits are used to check whether there has been some modification. This is what we call the syndrome of the state. And this is the nice idea. It only involves measuring part of the information, so you don't lose it completely. And with the information that you extract from this measurement, from this syndrome measurement, you can reconstruct the original state. So this is the idea. It's similar to what you have in classical computing, but it has some subtle modifications.
Right. Now let's talk about quantum advantage a bit. The term quantum advantage or supremacy gets a lot of attention. How would you define quantum advantage rigorously? And can you cite examples of problems or tasks where even current noisy quantum devices might outperform classical ones?
I would say that you can think of quantum advantage in several different ways, and maybe this is kind of where the controversy arises, because people talk about quantum advantage in different ways, meaning different things, and probably this leads to some confusion. So quantum advantage can be mathematically provable advantage for some algorithms, and we have this, for instance, for Grover's algorithm or for Shor's algorithm. In theory, you can prove that if you have a quantum computer with error correction and big enough and connect all-to-all qubits and things like that, then you can execute these algorithms faster than with a classical computer. And this is a mathematical fact, and there is no discussion about this. But then there is practical quantum advantage, the demonstration of, in practice for a certain problem, a shorter execution time with a quantum computer than with a classical computer. And this is the intention, or the way in which the idea of quantum advantage or quantum supremacy was introduced several years ago. But this is, for obvious reasons, something that is not mathematically provable, because you need to do this with a quantum computer, and you need to compare your results with the results of a classical computer. But classical computers are getting better and better every time, and new classical algorithms are developed that are better than the ones that we have now all the time. So quantum advantage in this practical sense is always a moving target, because what is a quantum advantage now may be not a quantum advantage 1 month from now, if someone comes up with a new classical algorithm that is better than the ones that we have now. And this has happened a lot. This is not something theoretical. For instance, in 2019, Google announced that they obtained this quantum supremacy or quantum advantage. for a certain problem that we will discuss later. And nowadays, you can solve this problem with classical computers. So this is not quantum advantage anymore. But then again, of course, Google and other companies improved their quantum algorithms, are their quantum computers, and now they have better results for that problem. So again, they are in advantage. And this is kind of a race to see who is better at a given moment. Of course, because for some problems, quantum computers are mathematically better. At some point, the classical computers will not be able to keep running better and better. Okay. But at the time, we are not there. So practical quantum advantage is something that is subtle and is not solid in that way. And another thing that we need to take into account in the book, we describe these experiments for quantum advantage with some detail, is that these are not practical problems nowadays. In the future, we expect to have quantum computers that solve practical problems much faster than classical computers. But nowadays, this would require error correction on big computers, and you cannot run Shor's algorithm. For instance, if you could run Shor's algorithm, it would be very, very easy to show quantum advantage, because you can check your results. If you have the factors of a number, you can multiply back the factors to see if you have solved the problem. So this is something that is verified. But we cannot run those algorithms yet. So we try to obtain quantum advantage with convoluted, artificial, academic problems that are really not useful, but they are things that quantum computers can do better than classical computers, even if nobody cares about them, except people who work in quantum advantage, of course. For instance, the kind of experiments that we talk about in the book, I think this is the last chapter of the book, are what are called random circuits. What you do here is you run a quantum algorithm and you check and see what are the results of running this random circuit. This might have some application in the generation of certified random numbers, which are useful, for instance, in cryptography. But this is a niche application, and it's not clear whether it is really practical or not. But apart from that, this is something that is not really useful for practical purposes. But this is something that a classical computer cannot do efficiently. So you can do it with a quantum computer, even with the limitations in hardware that we have today. So these are the kind of experiments that people are running.
Right. Got it. And conversely, and you hinted at this a bit earlier, but what are some of the most common misconceptions when claiming quantum advantage?
Yeah, I think it all goes back to this idea of demonstrating quantum advantage in practice. So you do it now, but if the algorithms change over time, the classical algorithms, then this is not quantum advantage anymore. And the other implication that I see people outside the field raising many times is that, well, quantum computers have reached quantum advantage, then I can solve any problem faster with a quantum computer. No, this is for a particular, very special academic problem. It does not imply that now you can, I don't know, solve molecules with a quantum computer faster than a classical computer. Eventually, we might reach that point, and we want to reach that point. But for now, this is only for academic problems.
Right. Got it. So now let's move on to our next segment. We'll talk a little bit about quantum software and engineering practices. Let's start by talking about programming abstractions. As quantum computing frameworks mature, for example, Qiskit, what programming abstractions have emerged? How do quantum circuits and gates, for example, map into classical programming? concepts?
Yeah, well, this is something that is usually surprising to classical programmers. I always remember the first student of mine from the the degree in computer science that got interested in studying quantum computing. He came into my office. He came through that door, and he asked, "Well, I'm interested in quantum computing. How do you implement a loop in a quantum computer?" And he was standing at the door, and I have said, "Please come in and sit down because I have bad news for you." So in quantum computers, in quantum programming, you don't have loops. You have circuits. These circuits are a finite amount of instructions, and they run in a certain amount of time, and they end. You cannot have them like looping or storing values or things like that. You just run them, obtain a result, and then you do something with that result. This is why many quantum algorithms do not work only on the quantum computer. You need also a classical computer to then post-process the results and things like that we discussed earlier with the idea of repetition of measurements and things like that. So it's kind of difficult to build abstractions on top of that. Because if you look at a quantum circuit, for people who are familiar with assembly programming, for instance, this is very similar to machine code, but without jumps or loops or conditions or things like that. So you have to decide in advance what are the instructions that you are going to have. And then you have a classical computer that, depending on those results, may run the same circuit or a different circuit and things like that. So to me, it's difficult to even imagine what kind of abstractions you can build on top of that. Of course, there are like certain families of circuit or certain subroutines, quantum structure subroutines that you can like monolithically build and use to obtain some results. For instance, the quantum Fourier transform that we were talking about earlier is very good to obtain information about the periodicity of data or frequencies. So you have that abstraction. Or amplitude amplification that you use in Grover search. This is a kind of technique that lets you like amplify the probability of obtaining a result and things like that. So those blocks, those functions, those subroutines are things that you can program and then you can use inside or together with other quantum programs or classical programs. The main difficulty for creating more abstractions of this kind is that quantum code needs to be run in a single run. You cannot like stop and extract information. If you measure in the middle of something, you lose all the information. So you need to run it completely without interaction with the environment or with other programs. So it's difficult to build things that you can reuse or that you can combine because they have to be black boxes in which you enter information and you extract information.
Right. And are there any emerging design patterns or standard libraries of quantum operations that developers can adopt to manage complexity in quantum code?
For instance, in libraries like Qiskit, you can find this kind of thing. For instance, in our book, we implement from scratch kind of this design pattern for Boolean functions, for oracles, but sometimes they are useful, sometimes they are not so useful. It depends because designing these functions, it's quite tricky. I'm not an expert in that, but I have collaborated with people. For instance, one of our technical reviewers is Francisco Orts, who works in designing quantum circuits for multiplication, addition, things like that to make this faster. There are several design patterns, but they are tricky. It's not something that you can like generalize too much, and then you discover, oh, I can reduce the number of gates by this nice transformation here. So it's not something that I think it's completely developed yet.
Okay, got it. And how does the notion of a quantum compiler or transpiler differ from a classical compiler? And what should a developer know about optimizing circuits for a given hardware backend?
Well, the notion of transpiling or compiling is very similar to the one that we have with classical programming languages. So you have a high level abstraction like C or Java or whatever, and then you translate this into machine code. So this is more or less what happens with with quantum computing. But the kind of language that we have now, for instance, Qiskit, is still very low level because, as I was mentioning, you don't have these loops or you don't have data structures or things like that. And it's difficult to conceive that you can even have this in the future. And at the same time, contrary to what happens with modern compilers, in which you can completely ignore the details, well, completely ignore. In most cases, you can completely ignore the details of the underlying hardware and you rely on the compiler and you know that it will optimize a lot your code. With quantum computers, sadly, you still need to know what is the kind of computer that you are running your code in. Because as we were discussing before, most quantum computers don't have all-to-all connectivity between the qubits. So for instance, if you are designing your circuit and you say, oh, I want to operate on both the first and the last qubit of my circuit and they are very far away, you can do that. And the transpiler will accommodate your wishes and will implement that. But this will translate in a lot of operations. So you only have one, but this translate in your code, you only have one, but this will translate into many, many, many different operations to move your data until you have the data in two qubits that are close to each other. And then there is an actual operation that the computer can perform there. And then you need to go back and move the data back to the original position. So if you are not aware of that, of course, you can write your circuits, compile them, and try to run them. And if you run them on a simulator, on a classical computer simulating a classical quantum computer, you won't have any problem. If you run this on the quantum computer, each of these operations will introduce noise, and you will obtain much worse results. So you need to be aware of the kind of operations that you can perform in the actual computer that you are targeting for your code. On the connectivity, for instance, even if you have a critical algorithm or operation that you want to run, you can also look, for instance, to the quality of the qubits. Not all the qubits have the same quality in the computer, and this quality varies over time. These quantum computers are calibrated on a daily basis, and then sometimes some qubits are behaving better than others. If you need good quality results, maybe you focus on running only on those quality qubits. So you need to know about it.
Right. And let's talk a little bit about testing and debugging. Given that quantum states cannot be directly copied or fully observed, how do developers test and debug quantum algorithms in practice?
Yeah, this is where classical simulation of quantum computers becomes very, very important. Because if you write your code, your quantum circuits, and you try to run them directly on quantum hardware, and you get strange results or unexpected results, you will never know whether this comes from the probabilistic nature of the measurements, noise in the machine, or an error in your code. Because you have all these three effects interlapping and working at once. So what people do is to first run the code in a simulator, in a classical computer, because simulators can be usually are designed to give perfect results. Because as I was mentioning earlier, what the quantum computer does is it takes a vector and it multiplies this vector times a matrix. So this is something that you can do perfectly with a classical computer up to a certain number of qubits. The problem is that once you go beyond that number of qubits, this is impossible because the amount of memory that you would need with a classical computer grows exponentially. For instance, we've been working with some researchers here in Spain to develop classical simulators of up to 38 qubits. And for that, we need 8 terabytes of RAM. 8 terabytes of RAM. If we would increase the number of qubits to 39, we would need 16 terabytes of RAM. So for 127 qubits, there is not enough memory in the whole world to simulate this. But up to 30 something qubits, this is something that you can execute perfectly without noise, without measurements in your computer. Maybe you need a supercomputer with a lot of memory, but you can do this. And then you can be sure that your code is correct. And then you can also run tests with noise with these simulators to adapt your code in order to run it on the quantum computer. So like the methodology is kind of first you run with a perfect simulator, then a simulator with noise, then you go to the quantum computer to isolate the different sources of errors or runs.
Right. And what kinds of bugs or errors are most common in quantum code? And does Qiskit have any specific tools for debugging such issues?
Well, of course, these simulators are like regular in classical machines. I mean, they are like regular computer programs. So any debugging tool that you can use to debug your regular classical code, you can use it to debug this. The most useful thing is to inspect the state of the vector at any given point in the program. Another thing that we use and we mentioned, for instance, in the book, is the possibility of having visual simulators of quantum circuits in which you can like drag and drop different gates in your circuit to quickly build a prototype. And then at any given point, you can like not perform a measurement, but actually see what are the values, the state of the system at that point without measuring. And this is very, very useful because after each operation, you can know what is the state of the system. Of course, if you are working with 20 qubits, for instance, this involves looking at a vector that has more than 1 million numbers, which is maybe kind of complicated, but at least you can do this. And to me, this is the most useful way of debugging the circuit. You also need to take into account that most of the time you work with circuits that are not too big or that have some structure that mathematically gives them some properties that you can guarantee. So you don't work with the full complexity of, I don't know, millions and millions of numbers flying around.
Right, right. Thank you for that. Now let's talk a little bit about reproducibility. Quantum computations yield probabilistic outcomes and results can differ, between hardware backends. How can developers ensure reproducibility of quantum experiments and simulations?
Well, they can't. They can't. It's impossible. You cannot reproduce something that is by nature probabilistic. But of course, what you can do and what any useful quantum algorithm guarantees is a certain threshold of success or probability of success. For instance, with Grover's algorithm, you know that, well, if you run this amplitude amplification for a certain number of iterations, you will have 99.9 probability of obtaining the correct result. But of course, you can be very, very, very unlucky and run this for 1,000 times and not obtain the correct result. It's very, very, very unlikely. But there is, I mean, by the intrinsic nature of quantum theory, it's impossible to ensure reproducibility. What you can ensure is reproducibility with simulations, because the simulators, of course, also include the possibility of performing measurements, but these measurements are pseudo-random and they depend on seed that you can set. So this is in that, for instance, we do in the book, we always set a seed for the simulations. And if you run the code with that seed, you will obtain exactly the same result that is stated in the book, as long as you use exactly the same versions of the libraries and all that. Yeah. So for simulations, you can do this because there is no true randomness. It's all through the randomness that comes from a seed that you can set.
Okay, got it. And now let's talk about developer experience. So Qiskit and other tools have come a long way, but what gaps do you see remaining in terms of usability, documentation, or tooling?
Well, I mentioned one of these limitations at the beginning of our talk when I referred to the quickly pace of change in quantum solving. So Qiskit changed rapidly. It used to be the case that new versions changed the API, so your code used to break very, very easily and very, very rapidly. Maybe after 2-3 months, your code was not working anymore if you updated your Qiskit version to the newest one. This has been greatly improved. In fact, I was very, very nervous because we started writing the book last year, and we knew that a new major version of Qiskit 2.0, was scheduled for around the time that we would be finishing the book. So we could not work with the new version because it was not out, and we could not know whether it would change. So I was really, really nervous because that could imply, and this is also why we separated the code into different chapters from the explanation of the protocols, for us to be able to implement changes quickly should Qiskit 2.0 be very different from Qiskit 1.0. But I was amazed at checking that with the new version, we only had to change our code in a few places. Most of it was running out of the box perfect. So this has come a long way. I think documentation still needs to be improved, not only for Qiskit, but for instance, for penny lane that we used in our previous book, because we need to take into account that people developing these libraries are usually volunteers. Of course, people at IBM are working on this, but and at Xanadu, which is the company that develops Penny, but there are also many volunteer programmers working on this, and they don't have the resources or time to fully document everything. And since everything is changing so rapidly, some of the features are not completely documented. You need to go into the source code to know what it's really happening under the hood, which is something that, well, I'm now used to doing, but it's difficult every time. So this is why in this book and in the previous one, we try to give a lot of details about how things actually work. Because sometimes you cannot find this in the documentation, and there are subtle details. For instance, one thing that we discovered while writing the book is that when you introduce measurements in your circuit, you can do it in two different ways. You can introduce them, let's say, at the beginning, or to mention at the beginning what are you going to measure, or you mention it at the end. Depending on this decision, the name of the variable in which the results are stored is different, which was something that we didn't expect. So, and it took us a lot of time to discover what was happening. So this is something that we explain in the book. So people learning from our book won't waste time scratching their heads trying to know what's happening. So, well, this is a problem or problem. This is something that is not documented, but it happens this way. So you know, and you can cope with it. And I think this is something that needs to be improved. Yeah.
Okay, got it. And that brings us to our last segment, where we talk a little bit about quantum hardware platforms and the roadmap to utility, which everyone wants to explore. So my first question is, currently the quantum hardware landscape includes superconducting qubits, trapped ions, photonics, spin qubits, etc. Could you compare some of the leading approaches in terms of qubit connectivity, coherence times, gate fidelities, and scalability?
Well, I must say I'm not a quantum hardware expert by any means. My background is in quantum software and quantum algorithms. But I mean, as I mentioned, you need to know a little bit about the hardware you are running your programs in. Otherwise, you will get results that you cannot explain and that are completely unexpected. So what I've learned in all these years working with quantum algorithms is that the different quantum technologies out there have different advantages and drawbacks. For instance, the one that you can use with Qiskit, you can connect to these online quantum computers provided by IBM, is based on superconducting qubits. And this is the leading technology nowadays because it's the one that is most similar to classical hardware. So most of the techniques of the building techniques for this hardware can be like copied or reused, repurposed from classical hardware. But it has some limitations. For instance, it has limitations in terms of how many gates you can run on these computers, because you mentioned coherent times. Coherent times refer to the amount of time that the quantum states remain in this superposition or entangled states, because they spontaneously, by interactions with the environment, can decay to something that is not in superposition or not entangled anymore. So these times are on the order of microseconds. They are very, very short. This is nowadays. So this is why you cannot run long circuits like the ones that you need for Grover's algorithm or for Shor's algorithm. Gate fidelities are getting very, very good, even with superconducting qubits. This is also very important in order to do quantum error correction, because gate fidelities refer to the accuracy of the operations that you do. So you do these rotations. Maybe you don't get all the way to the angle that you wanted, you fall short or you overshot. This difference is kind of the oversimplifying the fidelity of the gate. Now they are around 99 point something, which is much better than 5 years ago. So they are improving. So this is superconducting qubits, and they can scale quite well, not very, very well, but quite well. But then you have, for instance, trapped ions that you mentioned. Trapped ions have coherent times that are much better. They are much better, up to seconds, maybe even, which is orders of magnitude better than with superconducting qubits. But then, and qubit connectivity is also better, but then they are not so scalable as far as I know. So you can go up to several dozens qubits or something like that, but maybe not hundreds or thousands. Then you have photonic computers. Photonic computers maintain the coherence of the states also for a long time, and they operate at room temperature. One of the drawbacks of superconducting qubits is that they need to work at temperatures that are close to absolute zero, so millikelvins. This is very, very difficult to achieve, and it limits the operability of these computers. You cannot have them at home because you need something to cool down this to 0.5 Kelvin or whatever. So photonic computers work at room temperature. They work with photons. But then the operations are not easy to implement. For instance, the entanglement is difficult to achieve with these photons, as far as I know. There are other technologies, for instance, Rydberg atoms, neutral atoms. People at different places. For instance, I was doing some research at Harvard. People there are working with these cold atoms. Here in Asturias, where I live, a new project to develop a quantum computer based on Rydberg atoms is now projected, and these computers have other advantages. For instance, you can move this work by trapping atoms with lasers. And then they can move the atoms around with the lasers, what they call optical tweezers. So in this case, you don't have the problem of connectivity, because even atoms that are far apart can be moved to interact together and then move back. The problem is that this is slower than operating with, for instance, superconducting qubits. So each technology has some advantages and some drawbacks. My personal belief, even if I'm not an expert, so this might be completely mistaken, is that the technology that in the future will be used to implement useful quantum computers has not been developed yet. So there are many, many research teams all over the world working on different technologies. Probably the one that will be like the one that offers longer coherence times, better gate fidelities, better connectivity and scalability has not been invented yet. But, well, I don't know.
Right, right. But, are you by any chance aware of any upcoming hardware innovations? You talked about some new things, but are you aware of any that you find especially promising for future scalability?
Yeah, well, there is a particular one that I especially like, and that is receiving a lot of attention lately. As I mentioned, for instance, with superconducting qubits, you can scale your chips up to a certain number of qubits, maybe several hundred, but then it becomes difficult to go beyond that, because you need these superconducting qubits work by receiving the implementation of the operations is done by sending microwave pulses of a certain frequency. And each qubit needs to receive a different frequency, because if you send the same frequency to qubits that are close, then you operate on both, you obtain something that is not correct. So you can scale up to a certain amount of number of qubits, because each of these frequencies and each of these operate microwave pulses needs to be controlled, and this grows big very quick. So one proposal that I find very interesting is to have different chips that have maybe several hundred qubits each, and they are not connected directly together, only connected at the board. And they have a connection that is not so so tight as the qubits that are inside one of these chips, but you still can operate around the borders and create some entanglement, maybe not full entanglement, but some entanglement at the borders. So this is something that, for instance, IBM has proposed, and other companies too. And then people in the quantum computing community is starting to develop algorithms aimed at using this kind of chip, in which you have circuits that have dense connections, and then not so dense connections between different parts of the circuit. So you can run them on different chips and connect them together not so tight. So this is something that will help scalability, because you can build a lot of these chips and join them together. But then the algorithms need to adapt to this new kind of hardware, because you cannot entangle one qubit here with one qubit that is several chips away.
Right. Okay. And now the big question, Ian. Looking ahead 5 to 10 years, what do you consider realistic timelines for quantum computing to deliver practical benefits?
This is so difficult. I mean, I've been getting this question for many, many years now. I still find it very, very difficult to estimate. I really don't know. For some things have developed much more quickly than I expected. For instance, we are having now some demonstrations of implementation of quantum error correction with certain number of physical qubits implementing one or two logical qubits or even more, which is exciting. But at the same time, some of the problems that quantum hardware has had for the last 2 decades are still there. I was reading yesterday a paper by researchers at IBM in which they used their current quantum computers to solve problems in quantum chemistry. They claim that they have obtained the same kind of accuracy that you can obtain with classical computers in practical problems. So this is not quantum advantage, because it's the same performance that you obtain with classical algorithms, but you can match up these results with quantum computers. This is what they claim. They make this bold claim that they aim for practical advantage next year, 2026. To me, it's difficult to believe, but I mean, that would be amazing. That would be wonderful that you could, in 1 year time, solve this kind of problem with a quantum computer better than with a classical computer, especially because it's a practical problem of interest in drug design, in medicine, in chemistry. So lots of applications. Maybe I'm a bit more not so optimistic. I would say 5 years, but I don't want to be too hard about that. Maybe if you ask me next year, I will say 5 again. So who knows?
Okay. Okay. Yeah. And final question. What advice would you give to software architects and engineering teams who may want to prepare for, integrating quantum computing into their technology within 5 years? Say?
Yeah, I mean, that is a very, very good question. We work with a lot of companies that are trying to integrate quantum technologies in their workflows, even if they know that maybe they want practical results in the short term. But I think it's very, very important to start looking into this if you are interested, if you think that you can get some kind of advantage from quantum technologies as soon as possible, because this is not easy by any means. I mean, we've tried with both books to make it as easy as possible. I should say that according to the feedback that we have succeeded to some extent. So we try to make this as easy as possible, but it's not easy. I mean, even if you know Java and C++ and Python, Rust, and many different languages, this will help you to some extent, but quantum computing is completely different. There are no loops, there are no data structures, you cannot copy information. When you measure something, you ruin it. So you need to change your way of thinking about programming. So the sooner you start, the better. The sooner you start, the better. Maybe you won't get return of investment in the short term, but if you try to jump into the quantum train when it's already running, probably it will be too late, because the curve of the learning curve is very steep. I think it's a fascinating journey. I love it, but it's not easy. It's not easy.
Mm. Yes. That was an amazing conversation, Elias, and thank you so much for joining us and sharing your insights into the foundations and frontiers of quantum computing.
Thank you so much. It was really, really a lot of fun.
Yeah. And to our viewers, thanks for watching. If you'd like to explore the topics we've discussed in greater depth, check out A Practical Guide to Quantum Computing. It walks you through core algorithms, quantum protocols, and hands-on implementations using Qiskit, all with mathematical clarity and practical context. You'll find the link to the book in the description below. Until next time, this is Deep Engineering.